Hello everyone. In this video tutorial, we are going to simulate a micro electromechanical system or MEMS heat exchanger. This figure shows the geometry of a MEMS heat exchanger. The MEMS heat exchanger has several flow paths and the hot and the cool fluid flow in the alternative channels. Due to the symmetry, we are going to simulate one unit cell. This is one unit cell which is enlarged in this figure, and you can see that this unit cell has two channels. In one channel the hot stream is flowing, and in another channel the cool stream is flowing, and thus they transfer the heat with each other. We are going to simulate this MEMS heat exchanger and see how the velocity, temperature, and the conduction flux is distributed. So open COMSOL, click on the file, click on new, click on model wizard, then click on 3D, and go to the fluid flow, click on the non-isothermal flow, and select the laminar flow, then click on add. Now click on the study, select the stationary, now click on done. uh, Click on the parameters and enter these parameter here. This is the radius of the flow channel, and this is the mean velocity of the hot and the cooled fluid. This is the hot inlet temperature, this is the cool stream inlet temperature, this is the mean temperature, and this is the mean density of the fluid. You can type these parameters here, or you can just copy and paste from the text file, the link of which is given in the description. Now go to the geometry, and from here you have to select the micrometer. So select the micrometer from this drop down list. Now go to the right click on the geometry and click on the block, and type 100 in width, depth is 300. Let me, okay, this depth is 400, uh, 400, and height is 300. And now bill selected. Okay, now again click on the geometry, click on right, and right click, and then click on cylinder, and the radius of the cylinder is it's r, and the height is 400, and type 2r in the z position, 2 steric, 2 steric r. Okay, click on build selected. Oh, sorry, I think there is some problem. Yeah, you have to select this axis type is a y axis. Y axis means that now this should be extended in the y axis, not in the z axis. So click on the bit selected, and now you can see this cylinder is down here. Okay, now click on the geometry, go to the transform, click on copy, and here copy this cylinder, click on cylinder 1, and type 2 steric r here, and 2 steric r here. Click on build selected. So this cylinder is now copied here as well. And now go to the boolean and partition, and click on boolean partition, and click on compose. Okay, click on compose and select all by control A. Okay, and just type this formula here. Type this formula here, block 1. This is actually block 1. Then cylinder 1, this cylinder 1 plus this copy 1, which is cylinder 2 actually, plus block 1. So this means this block 1 steric cylinder 1 plus copy 1. If we just type this formula, so this will actually give us the intersection of all these geometries. So if you click on double selected, so we just obtain the intersection. However, if I add the block 1, BLK1, BLK1, and build selected, so now I get this which is our required geometry. Now click on the definition, click on explicit and type solid in this label section and select the domain number 1. Now again click on the explicit and type cold channel here, select domain number 2. Now again click on the explicit and type the hard channel and select domain number 3. Now click on this icon union. Okay, click on this add symbol, select hard channel, cold channel and hard channel, click OK, and let's call this as a channels. Okay, now in the definition toolbar, click on the adjacent definition adjacent and write channel walls here, channel walls. Okay, and from this add icon, select the solid and channels, click OK. Okay, now uncheck the exterior boundary and check the interior boundaries. In this way, we actually define the boundaries of the channel, the cold channel and the hot channel. Now, click on this in the definition toolbar. Click on this local variable and select the domain. From here, select the channels and write row underscore W here in the name and enter this expression. So this is nothing but the fluid density. Okay, this relation, this expression will be used for the calculation of the fluid density. We have already provided this rho mean W, this steam, we have defined this steam in the parameter section. So this equation will be used to determine the density at any temperature, density of the liquid which is flowing in these two channels. Okay, now we have to add the material. So for that, go to the home and then click on the material, click on add material, and here type steel I4340, click on search and double click on this material, steel AISI 430. Okay, this is added here, and now search water, select the water liquid, double click, so the water is added here as well. Okay, now close that material window, and if you now click on the steel AISI 4340, this material, and assign solid domain 1. So this is the solid domain. That means that this is made of steel AISI 4340. So the COMSOL is now handling this as this steel material. Okay, now click on this H2O and from here select the channels. So on COMSOL, COMSOL now consider these channels as the liquid water. Okay, now click on this laminar and laminar flow, and from here select the channels. Okay, and now right click on this laminar flow and select the inlet boundary. So this is the inlet of the cold fluid, boundary number 5. From here select the fully developed flow, because we assume that this is the flow is fully developed at the entrance, and enter the mean velocity, which we have already provided, mean velocity of the cold fluid. Sorry, this is the velocity V mean, and now again select the, okay, you can select that boundary from here by clicking right on this laminar flow, or you can select this from physics boundaries and this inlet boundary. Okay, so this is the inlet of the hard fluid. Okay, boundary number 15, and again from here select the fully developed flow and enter the V main here. Okay, to go back to the depart view, just click on this icon, and we also have to define the outlet. So from this boundaries, click on the outlet. So this is the outlet of the hot, and this is the outlet of the cold. fluid. Okay, and we also need to define the symmetry boundaries, because we have assumed that these are the symmetries, this one and this one. These are the symmetry boundaries. So from boundaries, select symmetry, select boundary number 4 and boundary number 17. These are the symmetry boundaries. Now click on the heat transfer fluids. Okay, and select all domains. Okay, and now in the physics toolbar, click on the domain and click on the solid. Okay, and this is solid domain, domain number 1. You can set it from here, or just click on this domain number 1. So this solid is actually assigned to this this solid one is actually assigned to domain number 1. Okay, now click on this fluid 1, and you can see that channel, this domain 2 and domain 3, this is by default, this is assigned to fluid 1, because we have earlier we have assigned the solid domain to this solid to this domain number 1. Now go to this fluid type, select gas liquid. Here you have to select user defined and write a rho underscore W here. This is the density of the water flowing in these two channels. Okay, and this gamma, this should be also user defined and the value is 1. Okay, now we have to define the boundary condition. So for the boundary condition, go to the boundaries and select the flow condition, inflow. Again, inflow, we have two inflow. This is for the hot and this is for the cool, this is for the hot. So click on inflow 1, select boundary number 5, and in the upstream temperature, enter T underscore cold. This is the cold temperature. And inflow 2, so this is the boundary number 15, this is the hot inlet, so write T hot. Okay, and we also have to insert the outlet boundary condition. So for data, click on the boundary, in the flow condition, select outflow. So this is the out boundary number 15, this is the outlet of the hot fluid, and this is the boundary number 11, this is the outlet of the cold fluid. Okay, now go to the mesh, this mesh, and here select the boundary, select the free triangular, and the boundary is the channel walls. Okay, now right click on this free triangle and select size. Okay, click on the custom and click on this maximum element size and enter 10 here. The maximum element size is 10 micrometer. Now click on the free tetrahedral and click on build all. Okay, you can see that we have a finer mesh near the boundaries and a coarse mesh away from the boundaries. The reason is that near the boundaries, the mass and the heat transfer is very sensitive. So that's why I have selected a finer mesh near the boundaries. Now go to the study 1 and click on the compute. So it will take some time. Now let me pass. So this the default result is the velocity magnitude, the slice of the velocity magnitude. So you can also see this velocity, like if you click on the right, go to the volume, you want to see the velocity profile, and click on plot. So this is the velocity profile. So this is the velocity profile of the cold fluid, this is the velocity profile of the hot fluid. So you can see that the velocity is higher in the middle, and as we move towards the boundaries, the velocity decreases. Okay, you can see the temperature profile as well. Go to the temperature and click on the surface. So this is the temperature profile. Okay, you can change the color theme. So just click on this color table and click on rainbow and select the rainbow light classic. You can select any color theme. Okay, so this shows the cold stream and this shows the hot stream. So you can see that the red color is the highest temperature 300 degrees C, and this blue is the lowest temperature, which is the 300 degrees C, and this red color is the highest temperature, which is 330 Kelvin, sorry, not degrees C, Kelvin. So as the hot fluid moves along the this channel, so its temperature is decreasing, while temperature of a cool fluid is increasing. Okay, now click on this isothermal contour, click on the isosurface. So these are the isosurfaces. You can actually see the boundary layer development. So this color shows this temperature. That in this whole area, temperature is 301, while in this area, the temperature is 304, and in this whole area, the temperature is 307. So you can see that as we move forward, the thermal boundary layer is developing. Similarly, you can see the thermal boundary layer development in the hard channel as well. Okay, this is 329 temperature. This whole layer, this is 326. Now this is for 323, and so on. Okay, now in this isothermal contours, click on this streamline. This streamline, and they click on this replace expression, heat transfer in fluids, domain fluxes, conductive heat flux. Now from the streamline positioning, select this starting point control. Okay, the coloring and style line is this type is tube. Okay, radius scale factor, check this, and the point style, this is arrow. Sorry, this is arrow. Now click on plot. So you can see the conductive flux. You can see that the heat is transferred from the hot fluid to the cool fluid. Okay, so the streamlines actually shows the isosurface shows the temperature. These are the isosurfaces, and these streamlines show the conductive heat flux. Thank you very much. I hope you have learned something new today. So please subscribe the channel for more updates. Thank you.